Okay, here we go. Explicit versus implicit. Last year we talked about different ways of writing functions. We didn't spend a lot of time on it. But explicit versus implicit. Explicit is you have basically y is isolated. You have y isolated. So you have y as a function of x. So you have y as a function of x. So when you go to take a derivative, yes, you're taking the derivative of both sides, but you almost always end up with, or you can end up with, dy dx equals, and then for this side, you go ahead and use your rules. And that's what we've done up until this point. We've always had y by itself. So we've had y equals or f of x equals and then a function, and so then we take a derivative, no big deal. It's dy dx, it's f prime of x, and then you use the rules on the right-hand side. What's different when we have implicit is that we have a function in terms of x and y. What does that mean? Well, there's x's and y's in the function itself. It's not just, well, let's put it this way. Y is not isolated. You guys saw that yesterday. So if y is not isolated, we need to go ahead and, it's kind of hard to show this generally, so I'll just go ahead and try to give you the main idea. So we just need to take the derivative of both sides. And as we take the derivative of both sides, we need to definitely think about on both sides using our rules. Derivative on both sides using our rules. So explicit versus implicit, it's not really a huge deal to look at a function and say, hey, this is what's going on, as to what name to give it. But it is important to know how to go about taking the derivative. But the nice thing is, kiddos, if you remember from what I just said a little bit earlier, the process really does not change much because when we were going straight, once again, to dy dx, technically we were taking the derivative of both sides. Now, I do have steps on the next page about like the approach to take. Maybe the approach isn't the right way of saying it, but the point of attack whenever you see an implicit function. But once again, the big idea to remember is you're just taking the derivative of both sides, legally using the rules. And whenever you take the derivative of a y expression, you need times u prime, or times y prime, or times dy dx. Okay. I think you don't really need to skip any lines. I just did it for aesthetic appeal. The one that's super obvious is number 1. Do I need you to skip? I don't think I need you to skip a line there. We'll just write our d dx on both sides of an equals sign and leave it at that. Our 2.5 homework is due tomorrow. Because we're finishing the section today. If for any reason that changes, I'll let you know, but right now I'm planning on grading that one tomorrow. So you guys, we're starting a new chapter. You've turned in your homework spiral. What's done is done from chapter 2A. So just resolve and new and afresh. And we all need that, right? We all need to renew our resolutions, resting on grace. But pursuing responsibly the task given to us. Go ahead and just kind of resolve and and be like, okay, I'm going to start this homework and work on this homework and start this chapter off right. Guys, help me out. Differentiate. What's that word mean? To derive. To derive. To derive. Good. As you guys write that down, let me go ahead and try to reinforce something on the board. You don't need to write this down unless it helps. Why don't you guys look at those examples on the board? Not that you need to write them. Now go ahead and just for sake of those people who are gone today, I don't know why I wasn't thinking about it, you write it up here as well. What if my directions were to find the first derivative, aka to find dy dx, for each of these? Want to write them? You can, but I don't mind you guys just totally sitting back in the sense of not having to stress about writing and just thinking through with me. How would we take these derivatives? Now I had to change a few things because y wasn't supposed to be by itself and c and d. I'm trying to model some implicit equations, just a basic one. I'm not saying y couldn't be solved for on itself. Let's go ahead and just look at these really quickly. Question. From chapter 2a, how would we need to take this derivative? Raise it to the 10th power and write it out 10 times and then FOIL a lot and get a polynomial and then take a power rule of every single term left over.
Power rule and chain rule.
Alright, let's do it. Let's use chain rule and power rule. We can think about 2x plus 5 as a u. So we can think about this in rewriting in a sense as y equals u to the 10th if it helps you to rewrite. U equals 2x plus 5 and what is u prime?
2.
So then what would be the derivative of u to the 10th?
10u9.
10u to the 9th times u prime, right? So we need a u right here, and we need a u prime right here. So we would go ahead and bring down the 10 and keep the 2x plus 5. And then we would multiply times 2. True?
Yep.
Okay. So the derivative of u to the 10th is 10u to the 9th times u prime. Now, yes, we can simplify it, but for right now, there we go. Just leaving it at that. Now, letter B. Well, let's go to letter C first. How would we take the derivative of this? Pause. Don't get y by itself. Deal with it implicitly. So what am I doing right now?
You're taking derivatives of both sides.
Which I technically did here because the derivative of y is dy dx. And the derivative of this one is what we did. Okay, so we're deriving both sides. What's the derivative of x squared?
2x.
Good. Technically 2x times 1. But yeah. What's the derivative of y to the 10th? Pause.
Wait.
It's really u to the 10th when u is equal to y and u prime is equal to
So y is always going to be like a u. Okay.
whatever you're taking a d dx. So 10 u to the 9th times u prime. This is my u, and this is my u prime.
Oh.
Just like we did over there.
Oh.
So it's 10 u, which is 1, to the 9th times u prime. Do you see it?
Mm-hmm.
Now what would we need to do in order to finish? Get dy dx by itself. Equals 2x over 10y to the 9th. Technically we could make that 1x over 5y to the 9th, right?
Yeah.
But then with that we're good. Now technically we could go back to the original equation if to make it match with the back of the book or with a multiple choice answer if they have it only in terms of x or if somehow it looks a lot different than this. Somehow they used this equation to plug in. X squared equals y to the 10th. Somehow they used that to plug in and substitute and change it up. But otherwise we could just leave it like that. Now, what's the rule for taking the derivative of ln of u?
1 over u
One over
prime.
prime.
So in this one, I could think of this as an ln of u when u is equal to x squared plus 1. And what's u prime equal? Derivative of x squared plus 1 is 2. We take the derivative. I'm doing it to both sides, right? The derivative of y is dy dx is technically 1 times dy dx. The derivative of the right-hand side, I'm going to use the ln of u rule, which you guys were right. 1 over u, which is x squared plus 1, times u prime, which is 2x. So I have my 1 over u and u prime, which ends up equaling what's going to change when we go to something that's implicit. A little different, but similar. Sean?
I have a question for letter D. Couldn't we just use
E to the power of?
e to the power of and then
Yeah.
get y by itself and then be a little easier?
It could be a little easier. Let's see, though, if all of your multiple choice answers had x's and y's and a derivative, they did not get y by itself.
Okay.
Does that make sense? They probably won't give you one this easy. I'm just trying to see if we can deal with it implicitly, aka don't get y by itself.
I roll.
So what would I do?
Both sides.
Good, and so Tyler's already saying the derivative of 3x is
3.
what's the derivative of ln of y? Wait, what's the
1
derivative
over
of
y
ln of
times
u when u equals y and u prime equals dy dx?
1 over u times u prime, so 1 over y times dy dx.
We're using the same formula, 1 over u times u prime, plugging in 1 over y times dy dx. But we have to get dy dx by itself. So how are we
Multiply both sides by y.
So you could say dy dx is equal to 3y. Now, as Sean said, we could come back up here and we could go ahead and take this expression 3x equals ln of 1. We could set both sides e to the power of y equals e to the 3x. So what's another way of writing this? You could say it's 3e to the 3x also. But implicitly it would just be 3 times 1. So it would be one of those, if you have an implicit function all mixed up, look at your multiple choice answers and say, are there x's and y's? Okay, derive both sides. Are there just x's, like this one would be? Okay, solve for y, and then go ahead and take it. Or, if it's too hard to solve for y, solve implicitly, which I think we'll see some examples today and maybe tomorrow if we have some tricky ones we're looking at. Solve implicitly and then look to substitute. Oh, we didn't talk about our steps. And we already solved this one because we're amazing like that. So hold on, let me get rid of him.
Nice job, warriors.
So what is the key to starting implicit differentiation? Derive both sides, or differentiate both sides. They're synonyms, right? So we're going to take d dx. We're going to take d dx of both sides. Yeah. We're going to derive both sides, we're going to take d dx of both sides. Now if it changed, if they wanted d dt, we could do that to both sides also. But if it's an x, then we do d dx. Then, do you guys notice that we're trying to get dy dx alone on those examples? So if we're trying to get dy dx alone, if it is in multiple terms or multiple pieces, my advice, get all the dy dx terms by adding or subtracting on one side. Get all the non-dy dx terms on the other side for the goal of getting dy dx alone by factoring, and then solve. And that was what we had to do in that crazy example from yesterday. I don't think this is going to work. Let me try. Oh, it does work. There we go. This crazy example from yesterday, after we derived, no, not that one, that was easier. This one. We ended up with dy dx's in multiple places. Do you see how I followed the steps in that I kept the dy dx terms on the left as I moved the non-dy dx terms on the other side by addition and subtraction? Then I factored out the dy dx that I solved. Okay. That's the process. But where are you going to get most tricked? Probably right back here in the very beginning. Remembering when you take derivatives that every time you derive anything, you're deriving something with a y, you have to have a times dy dx. Okay. already talked about that, right? What's the remember? A function is not differentiable. What's it mean if a function is not differentiable? Write down the remember, maybe not the technical. I'll be write down the technical. I've been talking about that a lot yesterday and today. But the remember? Not differentiable, I heard someone say it. I'm sorry, what does it mean? Not able to be derived, or, here's a better way of saying it, where the derivative does not exist. So you can still have a derivative function, but it's like a discontinuity of the derivative, a domain problem of the derivative. A function is not differentiable. The derivative will not exist when it is not continuous. We already know that. The function is not continuous. It's not differentiable. Forever card number 9. Actually, don't remember. It's not 6. It's past 6.
7 was problem solving.
The connection between continuity and differentiability. Yeah.
Is there a convenient mathematical way to write conceivable?
It's moving. No.
Oh.
Found out like CONT abbreviating it, but otherwise it's the same. A function is not differentiable when it's not continuous, that's condition A. If it's not continuous, it's not differentiable, right? Or when the tangent line would be vertical, that's B. Or when the tangent slopes don't agree, that's C. A is not continuous, B is a vertical tangent line, C is the tangent slopes don't agree, that would be a sharp point. You have it in your forever card. You can also reference forever number 9 if you want to put that in parentheses and basically not even write most of that. But vertical, that would be like a denominator equaling 0 of the derivative. And tangent slopes not agreeing would be like a piecewise function that doesn't match up for f prime. Okay. That's going to show up a little bit in homework because I think we talk about differentiability just a little bit as we get into more examples. Yeah, we have a lot of examples. We better get going. You ready? Set and go. Alright, cool kids. Take the derivative of both sides. I'm going to follow up pretty closely, but I'm going to try to say closely and quickly at the same time. Anyway. Yeah, I know that's that. Derive both sides. Try not to do all of these examples. Right now, derive both sides. And for my ones that were trying to get y by itself. Not this one. Be a bad idea. Once you think you have the derivative, go ahead and look up here. Before getting dy dx by itself, pause. Many of you made one of the most common mistakes. Well, there's 2 common mistakes in this one. How many of you guys got and wrote down 3x squared?
Yeah.
3x squared. Who wrote down 3x squared? Good. How many of you guys wrote down 3y squared dy dx with the dy dx? Now, how many of you guys raise your hands if you used the product rule at all? Ooh, okay. Fewer hands on that one. That's okay. That's a struggle. Product rule. Some of you guys are like, leave the 3. You could have left the 3. The other way of doing this would have been to leave the 3 and just have the second by squared, the first bx. You could have done that as well. You would have second d first plus first d second. If you look at this, it'd be the exact same thing because you distribute the 3. So either way works, to leave the 3 as the constant and to have the second by squared, the first bx. But I tend to look at this and be like, ugh, I'd have to do an extra step. I like to group the 3 in with the x because that way it's already distributed in. Product rule. We had to do it because it was 3x times y squared. Does that make sense? 3x times y squared. So second d first, y squared times 3. Plus, first d second, 3x times 2y dy dx. And if you have that, something you needed to correct a little bit. If you have that, now what's our goal, guys? I'm going to move it all to the left side just because I'm used to moving dy dx to the left because I want to write it to the left as the final answer. So I'm going to go ahead and, let's see if you can follow my logic. Keep the 3y squared dy dx. Subtract the 3x squared. Keep the 3y squared. Subtract the 6xy dy dx. Let's pause and let's check. I did a lot of algebra without showing it. I subtracted 3x squared because he did not have a dy dx. I kept him because he did. Then I went to the other side. And I kept the 3y squared because he does not have a dy dx. And I subtracted 3 times 2 is 6xy dy dx to the other side. Does that make sense, Sarah?
So if there's like multiplication, you have to do power 1, you can't just use like forms.
You have to use the product rule. Yeah. Yeah. So, but only when it's multiplication of variable expressions. If it was like 3 times x, we could use the constant multiple. But since it's x times y squared, we have to use product. Does that make sense? Now, do you guys remember from your steps or even from the other example, what do we do if we're trying to get dy dx by itself? Factor. Pull it out. So pulling out dy dx, I need him totally alone, so I'm not pulling anything else out. Why did I write him up there? Because what am I getting you ready to do? Divide. Let's move this guy over. Now once you get everybody situated, you can go ahead and look and say, is there anything in common I can pull out? And would it help? We can pull out a 3. I would maybe even pull out a -3. I don't know. Maybe not. On bottom, we could also pull out a 3, right? Negative x squared plus y squared. They might write it y squared minus x squared. Same thing. We could pull out technically a 3 and a y, I suppose. Y minus, no, not y squared, sorry. Y minus 2x. 3 is reduced. I'm not really sure there's much more to do after that. You guys okay if we just box it in? How many of you guys on the test had problems on at least one making it match? Okay, yeah. Did you feel the tension that I've been explaining every time I say make it match? You could have a right answer. Not maybe you made a mistake and one of the rules went wrong. But you could have a right answer, but you have to make it match. There's an interesting similarity in life. Here's an interesting similarity. From what you've been through, from the experiences that you've had, could you think something is true or like this is a certain way that I'm supposed to live? Yes. Could someone that's coming from a totally different background, with totally different perspective, a different, what we would say in Bible classes, worldview, different experiences, could they come towards a situation or even towards life in general with a certain perspective of how they're supposed to live as what's true? Yeah. If you try to explain, hopefully what I would say, or if I try to explain why I live my life based on the Bible to someone coming from a totally different direction, well, I would say I need to keep the truth, but I might need to change how I express it or how I explain it or how I talk about it with someone because they might be coming from a totally different direction. So we need to keep it true, we need to keep it the same, but I need to kind of change how I give it or how I approach it or how I witness or how I talk or how I love on people, right? Same thing here. You can have something that's true, but it could be expressed a different way. It could be shown a different way. And maybe that has to do with some sort of substitution that could get plugged in. Maybe that has to do with some sort of simplifying. Maybe that has to do with like they wrote it different ways. So you just have to be discerning. Ooh, good word. be discerning to look at your answer and say, okay, this is what I have. Number one, have I done it correctly to the best of my ability? But number two, is there another way of writing it? And how did they get those answers? And is there a way that I need to change my simplifying to change or to plug in? So anyway, that's a good life skill too. If some of you are like, I don't even know it's true, and you're still trying to figure that out. But even after you're like, no, I'm pretty sure this is true, to the best of my ability, this is truth. You still have to think through, well, hold on, that's not going to necessarily correspond to how others see it. They might need to think of it a different way.
So another way of solving, couldn't we have canceled out the 3 y squared?
Ooh, that's a really good question. There are a lot of people that would think that that's true, and it would make total sense in their minds as to how to cancel it out from their past experiences. But the dilemma is that true? Is that legal? And the answer is no. And here's why. If we were to group the numerator and the denominator, the only way that you can simplify is you have to look at things like factors. And I can't put any parentheses anywhere else because there's addition and subtraction. So I can only put it around the entire numerator-denominator. Since these two don't match right now, I can't cancel out or reduce any. What made it different down here is that I was able to pull something out, so I could put parentheses around, and technically I could put parentheses around the 3 and the y and the 3. As soon as I have factors, which can be shown by parentheses, if they match, now I'm allowed to cancel. That's a great question though, because a lot of people would make that mistake even in calculus on a test. That's technically killing a kid. Yeah, Sean.
So, this is a question for homework. If we solve it a different way and like we have only y's, or if we only have x's, and we look at the back of the book and they did it differently,
I would say think of it as a make it match. On evens, you're going to do the best you can, leave it in whatever form you think they would have left it, which might just be the very first form you get with all the x's and y's. Odds, use that as a chance to be like, okay, making it match, get a feel for the homework, get a feel for the answers and what they're doing.
Okay.
And a lot of them, it's just going to be x's and y's, or if it's just x's, it was an easy solve for y quick at the beginning, which this one is not. So in this one, I would say leave it with x's and y's, because to try to simplify it, it'd be crazy. And if the answer key had something simplified, the first thing, if you're like, what, there's no way, you can't get y by itself, the first thing I would say is, hey, is there an x cubed plus y cubed? Because I could substitute for him. Well, there's not. Is there a 3xy squared? I could substitute for him. Well, there's not. But look at that, because every now and then that's how they make a crazy substitution. Tyler?
The AP tests, are they more like favored towards solving with implicit differentiation?
Yes.
Or
If it's written implicitly. Think like how we did square roots. We would rewrite it as the 1/2 power, but at the end we would almost always make it a square root again. How they start is usually how they end as far as forms. So if they start with implicit, they almost always end with implicit. But they could make one of those crazy substitutions I just talked about. Hold on, let me give examples real fast. I really want to get to this page. Let's do only one of these, guys. Which one looks scarier? Plug in your point to find a slope after taking a derivative, or the one with trig? Okay, so we'll do this one. The other one just says, hey, you're going to have x's and y's, so to plug in, you plug in the x and the y. That's the difference with plugging in.
oh yeah.
Let's do this example. And we'll do this all together for sake of time. It's written implicitly, x's and y's all over the place. So what are we going to do to both sides? Good. You guys see it's a chain rule on the left?
Yes.
Cosine is the outside. XY squared is the inside. So you could think about this if you want. You could rewrite it to be cosine of u. Maybe you want to take the derivative of the right-hand side because you know it's 1 dy dx. Maybe we should write the u over here, just in case. Some of you can do this all at once. Some of you, it's going to be a little bit harder. If u is x times y squared, Sarah, what rule are we going to use? Yeah. Does that make sense? Yeah. Good. So we can use first and second. Now, there were others of you that made that mistake in the last one. Did you see the product rule? Did you see the times? It shows up in the funniest places. Second D first would be y squared times 1. Just keep the y the same. You're not deriving them, you're just keeping them the same. But then when I go to do first D second, keep the x, but how do I take the derivative of y squared?
2y, 2y dx.
2y dy dx. So now I'm not even in this crazy problem, I'm just doing the u prime over here separately. So I can make it nice and pretty before I plug it back in. So I have 2xy dy dx. Now how am I going to use that u prime? Well guys, how do you get the derivative of cosine of u?
Negative sign.
Negative sine of
U.
u times
Times u
u
prime.
prime. I wrote this one out this time so that we could go ahead and see it before we plug in. Now it's time to plug in. Who was u? Good, xy squared. And who is u prime? Now question. A lot of you. And I've seen your papers in pre-cal, a lot of you, and in calculus, all of you. What do you forget to do? That is super important.
Parentheses.
It's times all of u prime. U prime is a quantity. U prime needs to be grouped. Yeah, that makes a difference, right? I've been telling you a long time to write those parentheses. To not kill seals and not kill puppies, etc. So now we need to get, ooh.
Do we have,
If I
we have to
distribute, you
distribute,
still get.
because we couldn't divide the entire thing, because then the
Yeah.
dy
If we divide, then he's stuck.
Yeah.
So we have to undo all the multiplications. We can add and subtract to get the dy dx's on one side. So we have negative y squared sine xy squared. You guys glad that you chose this one? It could get tricky. The negative can get multiplied by the 2xy sine of xy squared. I'm just moving the things outside in the multiplication, the terms outside of the sign. I'm moving it to the front to be easier. I'm not sure I'm going to move the dy dx's to the left this time.
Yeah.
What do you guys think we should do?
Just add to the right.
Can we just move it to the right, just to get them together real quick? So we're going to add the dy dx term to the right, leaving the non-dy dx term over here. Oops. Oh yeah, technically. Careful though. You guys see why I wrote a plus 1? Because it was this one plus that one, which is going to be a 1. So when I factor out the dy dx, let's see if you can follow for sake of time. When I factor out the dy dx and divide, I'm going to get 2xy sine of xy squared plus 1 as what would be there when dy dx came out. So what got divided over when I moved it by division? This is one of those problems you can show someone to be like, man, I'm doing hard stuff, right?
Oh, yeah.
And it's not really words. The words aren't hard. You knew to take a derivative. What was hard was the math, the rules, the solving. Guys, I'm not going to rewrite it, so dy dx is on the left. Is that okay?
Yeah.
Okay, then. We're going to go ahead and finish off class with just this quick little page, which helps. And we have some examples. We'll probably do workspace tomorrow, if that's okay. But we need to get down this page. This is the last bit of notes. Huh?
You group first.
Yeah, we'll just do group work. Group work at the beginning. Anything you can do in homework will be a huge help. And then group work can hopefully solidify that just a little bit more. You guys can catch each other's mistakes. What's different? What's new?
I mean, this is fun second.
We're finding the second derivative, which you would think is easy, and yet it's the trickiest part of implicit. And we've seen some tricky things with product rules, moving things to different sides, having trig, I would get down the blue. If you see a second derivative in homework, go look in the section for an example and see if you can do just one. All I ask is get in homework to where you're taking a second derivative and just do one. Then you can stop. Sound good? Do your homework until you get to where they ask you for a second derivative. Just try one while looking at an example. Then you can stop. Yeah. See, you liked it, huh? I think it was basically around like a solid that you can in the sentence, but no.